This says, let's find the solution. Excuse me. Of x double prime of t plus 6 x prime of t plus 5x of t equal 3 e to the minus 2 t. This is a differential equation, linear, second order, right? Would also fall under the category of higher order linear ordinary differential equation, also known as what? Higher order linear ordinary differential equation. That is also known as Holiday. Holiday. There you go. So back in the day, we already have techniques we could write a solution of this before by another method that we learn. That other method would require that we first solve this with the right-hand side equal to 0. We first solve for the homogeneous problem, find the general solution of the homogeneous problem, then find a particular solution, and then take a linear combination of both of those, which would provide us a solution of this. However, today we're going to proceed with those 4 steps. The first of those steps says that we should take Laplace transform in both sides of this equation. So let me rewrite the equation. So I'm going to write x double prime plus 6 x prime plus 5 x equals 3 e to the minus 2t. And what we're saying, step number 1, take Laplace transform on both sides. All right, so let's proceed to do that. Take Laplace transform take Laplace transform on both sides means that we're doing something like this. That's the fancy L. Laplace transform is linear. Okay, so that means that we could really write here Laplace transform of x double prime and then 6 times Laplace transform of x prime and then 5 plus 5 times Laplace transform of x and then the right hand side looks like 3 times Laplace transform of e to the minus 2t. Now, one of the things that we discussed last time is we also had a table last time. So last time we also had a table. If you will, you could complete the original table with the Laplace transforms of some original functions. But so you could add things to that table in which you can add what is the Laplace transform of the first derivative, second derivative, third derivative, and higher order derivatives, right? So in this case, once we proceed with step number 1, we take Laplace transforms. That involves Laplace transform of second derivative of x and Laplace transform of first derivative of x. Okay, so we're going to have to make use of these two terms on this table. Okay, so that's what we do next. In other words, let's see, we end up here. The first term looks like s squared x of s minus s. Maybe I should exaggerate this a little bit. So this is, let me write this again. This would be s squared big X of s minus s little x of 0 minus little x prime of 0. That takes care of the Laplace transform of the second derivative. And then we have plus 6 times, I'm going to write some expression here, 6 times little s times big X of s minus little x of 0. That will be the Laplace transform of the first derivative. Let me just confirm that. So we're looking at Laplace transform of first derivative, right? And so that says s times big g. Well, in that case, we're using x, right? And then little g, which would be little x. That would be the original function. That's what we have for the first derivative. So that's what's inside this parenthesis. And then we have plus 5 times Laplace transform of little x, which is big X of s. So that takes care of the left-hand side of this equation. The right-hand side, so I'm going to have to write here the equal sign. And then we have 3 times the Laplace transform of, this would be 3 times Laplace transform of this exponential, right? Laplace transform of an exponential, so that we have here Laplace transform of an exponential. The exponential has argument minus at, which means that that number a is going to be in the denominator, right? So that will lead to having here 1 over s plus 2. That 2 comes from the fact that there we have e to the minus 2t, so that's the number 2 that we write there in the denominator, which is in the right-hand side of this. So what proceeds next, what follows next, is to solve. You had a question?
Yeah.
Would you please press the mic? Yeah.
Since a is negative, would you have to change the sign for the denominator?
Yeah. The way this is written, that's a good point, but you wouldn't, because a is not negative, because the argument, that's true, we have e to the minus 2t, okay? Now, let's take a look at the table. And the way this is phrased here is e to the minus a t, right? So that a is 2, is not negative 2, okay? So that means that in the denominator we would use 2. If we had e to the 2t, we would write it as e to the minus 2t. And then we'd have to have that in the denominator, as you said, s minus 2. Or the other way to remember is you want to read this and you use in the denominator the opposite sign. So if you have e to the minus 2t, then you have plus 2 in the denominator. If you had here e to the positive 2t, then you have there s minus 2. So that could be one way of remembering. But the way it is right now, we use a equals 2. So we have e to the minus 2t, and then its Laplace transform has a plus 2 in the denominator. But that's a good detail because all the signs, everything has to be lined up here. So so we're going to clean up this a little bit. Here comes a stage in which we want to plug in the initial conditions, right? So we want to plug in initial conditions. So let's write some extra steps here. So we have s squared big X minus s times something minus something plus 6 s big X minus 6 times something plus 5 times big X. This is all equal to 3 over s plus 2. So the initial conditions would be by plugging in values for little x at 0 and little x prime at 0. So there are 3 spaces where we have things that we can plug in there. And those values, according to what we have in the original problem, are 1, x of 0 is 1, and x prime at 0 is negative 1. So we're going to evaluate here at 1 and negative 1, and then this value would also be 1. We're simply doing step number 2, evaluate, use the initial conditions. Okay? Use the initial conditions. So in the following step, so we have done take Laplace, enter initial conditions, and now we're getting ready to solve algebraically. We're solving for big X. So the next step is that we want to take this expression and solve for big X. Looks convoluted, looks messy, but it's not that messy. Look, X, big X is here, it's over there, it's in 3 places, and that big X is linear. This expression, relative to capital X, is linear. So, you know, this would be more complicated if that big X were inside of a logarithm or inside of a sine or cosine function, but it's not. So we collect those terms, collect all the terms with big X, and write them as a common factor, and then solve. So what we do next is that this expression so what we do next is this expression will be solved for, we're going to solve this for big X of S. That's what we do next, which means, next step, therefore, we can collect terms that are multiplying big X, and so those terms are going to include S squared plus 6S plus 5. All the other terms we can keep on the left-hand side of the equation, or we can send them on this step to the right-hand side of the equation. We may note here that this minus minus 1 becomes positive 1. Positive 1 minus 6 is minus 5. So let me write that one there as positive 5 on the right-hand side. And here we have minus S, so this would be positive S. And what else do we have? The original plus 3 over S plus 2. So what we are getting ready to do next is to solve for big X, right? But before we do that, let's manipulate this a little bit maybe. Let me work on this left-hand side. I'm going to write that's a quadratic in S. S squared plus 6S plus 5 is a quadratic in S, and I can write that quadratic in factorized form. Find two numbers and multiply that 5 and add up. They add up to 6. Those numbers look like 1 and 5. So we can write that quadratic as quantity S plus 1 multiplying quantity S plus 5. Now, the left-hand side, we can also write this as a fraction with denominator, common denominator, S plus 2. Numerator gets a little more involved, so that numerator could be written as S plus 5 times S plus 2 plus 3. So in the next step, we're ready to solve for X. We divide both sides by that quadratic that's multiplying big X, right? So we could divide this side and also this other side, divide that by this S plus 1, S plus 5. And so here we're going to end up with also S plus 1. Should write that over there, but I'm going to write it here, S plus 5. Okay? So that means that we could solve for big X of S. And this is going to look now as, I'm going to write the denominator as in order S plus 1 times S plus 5 times S plus 2. That's the denominator. And then the numerator, see the numerator we can manipulate, and that numerator you multiply S times S and S times 2, and then 5 times S and 5 times 2, you can end up with S squared plus, say, 25 plus 5S plus 10. And then there was a number 3 that was already there, this number 3. So this numerator actually stays as a quadratic polynomial, right? So this stays as S squared plus 5S let me step back here for a minute. Let's see where these terms comes from. That's not a 25, so let me explain. So if we multiply S times S, that would be S squared, and S times 2, that would be 2S. So let me make sure we write this clearly here. This would be 2S. 5 times S is 5S, and 5 times 2 is 10. So the quadratic is going to look like S squared 7S plus 10 plus 3, which is 13. Okay, and I'm keeping that denominator as the product of S plus 1 times quantity S plus 5 times quantity S plus 2. That's what big X is looking like. So what I'd like to do next is to use partial fractions to write the right-hand side as the sum, addition of 3 fractions, mostly because I want to turn to this table to when I reach the point of taking the inverse Laplace transform, I want to be able to use some of these expressions. And so it may be possible that that denominator, okay, that denominator I end up with is going to be of this type. It's going to be something times something 1 over s plus a, where a is to be determined. This is the type of thing you'd like to look for patterns there. When you're doing the partial fractions, maybe those denominators are of this type, s plus a in the denominator, or they may be of these other 2 types. These other types, s squared plus something squared, the sum of 2 squares, or the difference of 2 squares. So that's the type of pattern we are in the lookout for. Okay, so let's go ahead and use partial fractions here. So what we want, okay, so we want that to look like one number over S1 plus another number over S plus 5 plus, say, another number over S plus 2. This denominator here is precisely S plus 1, S plus 5, and S plus 2. That's what we want. So we need to work with that sum of those 3 fractions. Let's work then with that. So let's say, look, we add these 3 fractions, okay? We have the common denominator, that's where we're coming from, being s plus 1 times s plus 5 times s plus 2, so this would be a times s plus 5 times s plus 2. This would be b times s plus 1 times s plus 2. And then we have an extra term there, plus c times the product of the other 2. Right? This would be s plus 1 and s plus 5. So let me work with each. There are 3 terms in that numerator. Let me work with each of them. So we have a times s plus 5 times s plus 2. This is the same as having a times, okay, s squared plus 2s plus 5s plus 10. We had done this before. And this would be the same as having a s squared plus 7as plus 10a. Now, let me work with the next one, the one that involves the letter b, or the coefficient b. Okay? So this would be b times s plus 1, s plus 2. This is the same as b times the quadratic s squared plus 2s plus 1s plus 2, which becomes b times s squared 3bs 1s plus 2b. And we're going to collect all of these things, right? So then the last, so I'm simply doing this piece by piece. We had a times this 2, b times that 2, and then the last part of that numerator is c times s. So the last part of this numerator is c times s plus 1 times s plus 5, which means this is c times, excuse me, s squared plus 5s plus 1s plus 5. So we can write this as c s squared plus 6cs plus 5c. So we need to collect all terms with s squared, for example, right? So we need, here's a s squared, here's b s squared, and here's c s squared. So we're trying to collect that numerator. So that means that we can write those terms as in factorized form. S squared is the common factor, and we can write a quantity a plus b plus c multiplying s squared. So we can collect terms like that. Let's say we need the following. We need that quantity a plus b plus c times s squared plus quantity 7a plus 3b plus 6cs plus quantity 10a plus 2b plus 5c. We need that to be equal to 1s squared plus 7s plus 13. So this, in this equation, this right-hand side, so we need this quadratic, a plus b plus c times s squared, and then quantity 7a plus 3b plus 6c times s, and then 10a plus 2b plus 5c. We need that to match the numerator of the original calculation we started with. Let's go back. We go back a little bit here and see that numerator has s squared, 1s squared plus 7s plus 13. That's exactly what we're trying to match this quadratic to, which means this match is only possible if and only if we match the coefficients, right? So this follows, this is true if and only if we have a plus b plus c equals 1 and 7 7a plus 3b plus 6c equals 7, and the last part is 10a plus 2b plus 5c equals 13. So we have 3 unknowns, a, b, and c, and 3 equations. But these equations are locally linear.